All right, everybody, let's play a little game of sink or float here. I have this container here filled with a bunch of water, and I have some objects like this one right here, this little metal cylinder. Sink or float? What do you think? Let's just drop it in, see what happens, and it's going to sink right to the bottom. All right, I got another one here. I got this block, it's a pretty large block here. Let's drop it in, see what happens. All right, that one's a floater there. Why does one sink? Why does one float? Well, that's because of a property called density, and that's what this video is going to get into. It's going to get into the variables of density and the relationships between those variables of density. But let's look at a couple more. I have two blocks here. They're the same exact size. Same exact size. Let's drop one in, and we'll see that it sinks pretty easily down to the bottom. Drop the other one in, and, well, it almost sank, but it came right back up to the top. That's a floater as well. I got a couple different rocks here. Here's one rock, here's another. These two gray rocks. Let's drop one in the water. That went right down to the bottom. And that one went right down to the bottom. They're both sinkers. What makes the things on the bottom different than the things at the top? The things at the top, like this piece of wood and these other blocks, and this blueberry. Yep, that blueberry right there. The things at the top are less dense than the things at the bottom. And again, this video is going to get into what is density, what are the variables of density, and the relationships between those variables. So we're going to get to know density on two different levels. We're going to get to understand it conceptually, and we're going to get to understand it, how to calculate it. Let's get into it.
So why talk about density at all? You know, whether we're talking about a volcanic eruption or the ocean currents, or how to tell the difference between fake gold or real gold, or weather patterns, or even Arctic sea ice, it's all related to density. And so as we begin to talk about density, we're going to apply it throughout just about every single unit this year. It's a really important concept for us to get to know. So how do we define density? Density is defined by how much matter is in a volume. Two key words here. How much matter is in a volume. Let's consider a couple of different volumes here. Here's volume A, and here's volume B here on the right. And if we take a look here, this guy over here, volume A, has a lot more stuff jammed in there than volume B. But notice that the volumes are the same. We would say that volume B is more dense because it has more matter packed into its volume. How do we define matter? What is it? Matter is anything that has mass and takes up space. So if it takes up space and weighs something, I know weight and mass are a little bit different for this argument. We'll go ahead and consider them the same thing for this discussion. So for anything that has mass and takes up space, that's matter. You'd be hard-pressed to try to name anything that isn't matter. Volume, how much space matter takes up. So sometimes volumes can be large, sometimes they can be small. It's simply just how much space that matter will occupy, or how much space that matter will take up. And that can change. Think of a hot air balloon. Hot air balloon gets bigger as it goes up into the atmosphere and hot air is put into it. Some things get smaller, like the burning end of a candle or something like that, so the volume gets smaller. So we define volume as how much space matter occupies. So what's the equation for density? How are we going to quantify this, or how are we going to calculate density? All right, so we're going to use three letters here. D, capital, will stand for density. Little m, not big M. Little m will be for mass. And big V will be for volume. Because density is defined by how much matter, or mass, is in a volume. So we have our two variables right here, mass and volume. We're typically going to measure our mass in grams. We could use ounces or pounds or kilograms. Anything that measures the weight of something can be for mass. We're pretty much going to stick with grams. And for the volume, we're going to measure that either in milliliters if we're using a fluid, or we're going to measure it in cubic centimeters. What do I mean by cubic centimeter? All right, so if this box here is a centimeter all the way around, 1 centimeter times 1 centimeter, that's a squared centimeter. We need to have another dimension here. So if I did this, there's a centimeter squared, and if I did this, this is a cubic centimeter. And there we go. And what that means, it's 1 centimeter top to bottom, it's 1 centimeter front to back, and it's 1 centimeter side to side. And then what I wind up having is centimeters times centimeters times centimeters. And that equals 1 cubic centimeter. Now here's the nice thing. If I had a graduated cylinder here, and that graduated cylinder was filled with 1 milliliter of water, just 1 milliliter of water, if I were to pour this water into here, this 1 milliliter would completely fill this space. And what I mean by that is this. 1 milliliter has the same volume as 1 cubic centimeter. They are the same exact thing. 1 milliliter has the same volume as 1 cubic centimeter. We still haven't put the formula out there yet. So here it is. We have our density, and it's equal to mass and volume. Let's go ahead and clear this off, and I'll show you what we got. Density can be quantified, or you can get the numbers of density by dividing the mass of something by how much space it takes up. Or density is equal to mass divided by volume. We can shorten this up. D equals m over v. And we've probably already seen this a couple times in examples when we were going over 3 variable equations. And remember, again, we're going to measure mass in grams, and we're going to measure volume in either cubic centimeters or milliliters. And that 1 cubic centimeter is equal to 1 milliliter. They're the same exact thing. Let's take a look at an example here. Again, we have volume A over here, and we have volume B. Let's say these volumes, they're equal, and let's say they're each 100 milliliters. 100 milliliters. So if we take a look at our equation, density equals mass over volume, we have a constant here. So let's go ahead and make a little table. We have mass, volume, and this is for A, and this is for B. Let's take a look at the density of each one. So the volume is the same, 100 milliliters. And let's say that each one of these little things here weighs a gram. So if I count this up, I have 10 grams here. There's 10 little dots. And in here, there's 50. And again, I'm just saying that whatever these little things are, each one weighs a gram. So how do I solve this? Well, the density is simply the mass divided by the volume. So when I take the mass divided by the volume of thing A, what I'm going to get is 0.1 grams per milliliter. And for thing B, I have density equals mass divided by volume. I'm going to get 0.5 grams per milliliter. Which number's bigger? 0.5 is much bigger than 0.1. What does that mean? That this whole thing collectively is more dense than this guy right here. Even though they have the same volume, this has more stuff jammed into that volume, so it's more dense. And we proved it by using math right here, simply by taking that mass and dividing it by the volume for both A and for B. Let's take a look at relationships of variables. I'm going to introduce 2 new words here. The first one is going to be inverse. And what that says is as the value of one variable goes up, the value of the other variable goes down. And when we take a look at that, they're completely opposite. No matter what the variables are, as one goes up, the other one goes down. And that's very different than this guy here that says as both variables, as one variable increases or decreases, so does the other one. Or both variables either go up or they go down together. Meaning if you increase one, the other one increases. And in here, if you decrease one, the other one decreases. This is direct because they're doing the same exact thing. Inverse means that they're doing opposite things. That's what those relationships mean. So let's take a look and see how this applies to density. Here's our example again, where we had containers A and B. Here's A, and here's B. And if we calculate the density again, we can do that real quick here. Density equals mass over volume is our original equation. And if we remember back, we said that the volume for each one of these is going to be 100 milliliters for both of these. Okay, they're each 100 milliliters. We said the mass of each one of these little guys here is 1 gram. And in here, we had 10 of these guys. And over here, we have 50 of these guys over here. So now we can calculate the density. The mass of these, the mass for container A, or the density of it, is going to be 10 grams divided by 100 milliliters. And now let's take a look here. We know that that equals 0.1 grams per milliliter. Now let's take a look at it for B. We now know we have 50 grams per 100 milliliter. And the density of that is 0.5 grams per milliliter. And all I did was just take the 100 milliliters for the volume, the 50 for the 50 grams, the 10 for the 10 grams, and I divided 50 divided by 100, and over here 10 divided by 100. Now let's take a look at the differences between these. Again, this guy's more dense. 0.5 is more dense than 0.1, but look at what stayed the same. In both examples, this guy right here, the volume, stayed the same. The only variable I changed was the mass. I changed the mass of each one. Here, I made the mass go up. And look what happened to the density. The mass went up compared to this, and the density also went up. This would be a direct relationship. Because I increased the mass, the density also went up. And look here. Here we have a smaller mass, and we have a smaller density. And that is also a direct relationship. Let's take a look at an inverse relationship. Here we have our same examples again. So here's container A and here's container B. Change something this time. Container A has a volume of 100 milliliters. And it has a mass of 10 grams. Again, 10 little dots. Container B has a mass of 10 grams. But look at the volume. It's about half. So I'm just going to call that volume 50 milliliters. About half. Now watch what's going to happen here. Here's density equals mass over volume. And we know the volume of A, or the mass of A, is 10 grams. And the volume is 100 milliliters. And we've done this before. So we know that that's 0.1 grams per milliliter. Now let's take a look at B real quick. Here we have 10 grams divided by 50 milliliters. And when you do the math on this one, you get 0.2 grams per milliliter. Now look at what happened here. The mass remained the same for each one, 10 grams. And over here I have 100 milliliters. And over here I decreased this to 50. So watch this. The mass went down and it resulted in a higher density compared to this guy. This guy here had a higher mass and a lower density compared to this guy. So right here I decreased the mass by half and I wound up with a higher density compared to container A, where I had double the volume and I wound up with a lower density. And if I said mass here a second ago, sorry about that. I should have said volume. Smaller volume, larger density. Larger volume, smaller density. This is an inverse relationship. Inverse relationship.
So one last note about density and why we're talking about it. I know there's a lot to it on the conceptual level about what density is and on the mathematical level with the calculation, but it's really important for us to put out there why it's important that we talk about density. When we talk about the earth and we talk about minerals and we talk about rocks, density can be related to so much of what we see in earth science. When we talk about minerals, we can identify one mineral versus another by calculating its density. When we get into plate tectonics and the circulation of material within the earth, that happens because of density differences. We could talk about what happens at plate boundaries with plate tectonics, about when one plate smashes into another and the interactions that happen there and the volcanoes that are formed. If we talk about ocean currents and weather patterns, all that can be related back to density. We can apply this density concept to all the spheres of Earth and the interactions that happen between them. Hey, if you have any questions, let me know in class.